Hey everybody, I'm John Elliott Churchville, and today's Hump Day Power Thought is part one of a series that I call the Personal Expansion Principle. So I must begin by laying a foundation for what I'll be talking about later on in this series, and that foundation is a beginner's overview of quantum physics. Quantum physics, sometimes called quantum mechanics, is the branch of physics that explains how the particles that make up matter behave and the forces with which they interact. Accordingly, its venue is in the realm of subatomic particles, which cannot be seen with the naked eye. Quantum physics is the modern explanation for how atoms work and why chemistry and biology function as they do. From quantum mechanics, we learn how electrons move through a computer chip, how photons of light get turned into electrical current in a solar panel, or amplify themselves in a laser, or how the sun keeps burning. Although modern scientists can learn a great deal from quantum physics, it can also, and often does, give them huge headaches. For instance, there is no single quantum theory, which means scientists have had to innovate and adapt in order to alleviate their headaches. In the 1920s, Niels Bohr, Werner Heisenberg, Erwin Schrödinger, and others developed quantum mechanics, the basic mathematical framework that underpins theoretical quantum physics. It characterizes simple things such as how the position or momentum of a single particle or group of or few particles changes over time. But to understand how things actually work in what I prefer to call the apparent world in opposition to what others might call the real world, quantum mechanics must be combined with Albert Einstein's special theory of relativity. Now, Einstein's theory explains what happens when things move very rapidly. And it is his special theory of relativity combined with quantum physics that give quantum physicists the ability to create quantum field theories that alleviate at least some of their headaches. There are four fundamental forces of nature that govern everything in the universe: gravity, the weak force, electromagnetism, and the strong force. Now, there are actually three different quantum field theories that deal with three of the four fundamental forces by which matter interacts: electromagnetism, which explains how atoms hold together; the strong nuclear force, which explains the stability of the nucleus at the heart of the atom; and the weak nuclear force, which explains why some atoms undergo radioactive decay. Over the past 5 decades or so, these three theories have been brought together in a catch-as-catch-can way known as the Standard Model of particle physics. Despite the fact that this model on close examination appears to be held together by spit and chewing gum, it turns out that until recently it was the most accurate basic picture of how matter works that had ever been devised. The Standard Model proved its worth in 2012 with the discovery of Higgs boson, the particle that gives all other fundamental particles their mass, whose existence was predicted on the basis of quantum field theories as far back as 1964. Now, conventional quantum field theories work well in describing the results of experiments at high energy particle smashers such as CERN's Large Hadron Collider, where the Higgs was discovered, which probed matter at its smallest scales. However, if you want to understand how things work in many less esoteric situations, for example, how electrons move or do not move through a solid material and so make a material a metal, an insulator, or a semiconductor, things get even more complex. The billions upon billions of interactions in these crowded environments require the development of what are called effective field theories that challenge physicists to face and develop theories that will help them figure out solid state physics, and then there are issues that remain. And these issues are like, how come certain things can become semiconductors or electrical resistance pieces that work at room temperature? Well, beyond these practical problems lies a huge quantum mystery. At a basic level, quantum physics predicts very strange things about how matter works that are completely at odds with how things seem to work in the apparent world. For example, quantum particles have the capacity to behave like particles that are located in a single place, or they can act like waves distributed all over space or in several places. How they appear seems to depend on how scientists choose to measure them. And before they're measured, they seem to have no definite properties at all. This leads to a fundamental, insoluble problem related to the nature of basic reality itself. So let me give you an example. It's the paradox of Schrodinger's cat, in which, thanks to an uncertain quantum process, a cat is left dead and alive at the same time. Quantum particles also seem to be able to affect each other instantaneously, even when they're far away from each other. This is called entanglement, or in a phrase coined by Einstein, who contributed to but was critical of quantum theory, spooky actions at a distance. Even though these quantum powers are by no means completely understood, yet they are the basis of emerging technologies such as ultra-secure quantum cryptography and ultra-powerful quantum computing. In spite of all this, quantum theory has not been able to explain the first of the four fundamental forces of nature, gravity. Gravity remains the exclusive territory of Einstein's general theory of relativity, a non-quantum theory that does not even involve particles. Every intensive effort over the decades to bring gravity under the quantum umbrella and so explain all of fundamental physics within one theory of everything has come to nothing. Meanwhile, cosmological measurements indicate that over 95% of the universe consists of dark matter and dark energy, phenomena for which scientists have no current explanation within the standard model. And conundrums such as the extent of the role of quantum physics in life itself remain unexplained. What is known so far is that the apparent world is at some level quantum, but what is demonstrably clear is that quantum physics is by no means the last or best word about how the apparent world or the other worlds, which I have not discussed, alternative universes or states of matter and being that quantum physics experiments have alluded to or by implication have either predicted or confirmed their existence. So what's my bottom line point? Here it is. If the quantum world behind our apparent world is not objective, that is, it does not exist in isolation from our observation of it, but rather is influenced by our attempts to measure it, then the apparent world must not be objective to the same degree. This means not only that there is more than meets the eye when we contemplate the observable or apparent world around us, but also that we have far more power than we know to influence our apparent world. Now, I've raised these challenges in quantum physics to lay the foundation for a fuller discussion of how we can take advantage of what quantum physics has taught us and use that knowledge or lack thereof as a launching pad for initiating our own personal expansion as human beings. I'm John Elliott Churchville, certified speaker, teacher, trainer, disc behavioral analysis consultant, and coach with the John Maxwell team.